Hi there, I'm Hao, and this is just another video of me solving random numerical problem. So given an integer n, we need to count the number of possible unique binary search tree, which exactly n node, and the unique value from 1 to n. So if we have 3, then it is the all possible valid binary search tree. Okay, so if we have n is 3, which means we have like 3 possible nodes, right? Let's make it 4. Okay, so we pick that one as the root, right? Which means we don't have any option left on the left side here, right? And we have 3 options left on the right side, right? We pick 2 as the root. We're gonna have like 1 option left on the left, and then 2 options left on the right, right? If we pick 3, sorry, 2, right, 1, and 2. We pick 3 as the root. We're gonna have how many? 2 options left on the left and 1 option left on the right. Because only one number is greater than 3, and but 2 number is smaller than 3, right? Repeat 4, we have 0 option left on the right, but 3 option left on the left, right? So we need to do it for every single node. We need to test it, right? We need to pick each node as the root. So let's say we pick 3 as the root, right? Which means we have 2 options on the left, right? 2 options on the left and 1 option on the right, right? Which means we can do like 1, 4, right? Or 2, 4, right? But if we have 2 options on the right and 2 options on the left, we can also do 1, 5, and 2, 5, right? So it is the total combination, right, of them, which is equal to the total choice we have on the left. So, and the total choice you have on the right, multiply, right? This is the product of the total choice you have on the left and the total choice we have on the right. So in other words, it is the total number of possible subtree on the left multiplied by the total number of subtree we have on the right, right? So it's like left choice multiplied by the right choice, right? Number of right choice, number of left choice. And it is for only for one single root, right? And we need to also like add them together, right? So so it is similar to this. So like for example, right? You can have like red, green, or black, right? And then 1, 2, and then A and B, right? So you can either have like red. So any person can have like the combination, or they can pick the combination of either red, green, or black, right? And the red can go with 1 or 2. Same for the other 2 color, right? And the 1 can go with A and B, right? The 2 can also go with A and B, right? So on and so forth, right? A and B, right? So we can compare like the R 1B, right? With green to 1, right? Green to uh sorry, green to A, right? And black to B, for example, black to B, right? So we can combine them to have like a lot of combination, right? So we have 3 options here, right? 2 options here and 2 options here. So the total combination that we can make is 3 multiplied by 2 multiplied by 2, right? Which is 12 here. So we have a similar situation here, right? We have 2 choices on the left, we have 2 choices on the right. So the total combination that we can make is 4, right? But if we have like a tree, right, an empty tree, right, and it's only one way to make of a empty tree, which is no, right? If we have a tree node, and there is also one way to make the binary search tree. That is our base case there. Okay. So for example, right, if we have only 1, 2, 3, and we pick 3 as the roots, right? So 1 can go with empty, right, and 2 can go with empty. So 2 multiplied by 1 is 2, right? So this formula still work. It's the number of choice we have multiplied by the number of choice we have like on the left and the right, right? But the special case is when we have nothing or we have one thing. Okay, so let me rewrite this example so we have more space. So as we can see, the tree, each tree gonna have, it is a binary tree, right? So each tree gonna have 2 children. So that is 2 paths, right? And we need to go down for how far for like n level, right? In the worst case. So in that case, it is 2 to the n, right? But we need to do it for we need to do it n time, right? For each and every single uh I, the we need to pick every single number as the root, right? So that is n to the 2n. So this is the time complexity. We have O n to the 2n. Okay. So yeah, that's pretty much it, right? If the root is so let's make it a little bit simpler, so we don't have to draw too much here. So let's say we only have three elements, right? N is 3. So if we pick 1 as the root, right, we have 0 on the left, we have 2 options on the right. If you pick 2, then we have 1 option on the left and 1 option on the right. Similarly, if we pick 3, right, as a root, so we have 2 options on the left and 0 option on the right, right? This is our base case, so we return 1, right? And we need to add them together, of course, right? So if we pick 2 at the root, 2 here, right? We're gonna have what? Right? If n is 2, now n is 2, right? If n is 2, right, we're gonna have if n is 2, which means 1 can be the root and 2 can be the root, right? Right. Let me write here. 1 can be the root and 2 can be the root here. Right. So actually here we can split it into 2 cases. Right, 1 and 2. Right. And if we pick one as the root, what happened? We have 0 choice on the left, right? Oh, sorry. If we only have one element left in the root, right, we can just return 1. Return 1 here. Right. Return 1. Right. If we have 2 elements, right, we pick 2 as the root, which means we have 1 element, 1 choice on the left and 0 choice on the right, right? And we reach the base case, and we can just like return 1 here, return 1 here, right? And we need to multiply them together, right? 1 and 1. Right? If we have 1 choice on the left and 1 choice on the right, which means there's also only one combination that we can make, right? So 1 times 1 is 1. So number 2 here, we're gonna return 1, right? And now on the left side, also return 1 if 1 is the root, right? And so we need to add them together, right? We give us 2. So we can return 2 here, right? Just 2, right? 1 plus 1 is 2, right? Remember our array is 1 and 2, right? So we need to add them together because for each root, we can have the combination, right? If we pick root 2, which means we have like one choice on the left and zero choice on the right. Right? If we pick 1 as the root, right, we're gonna have a whole different combination similar to this. So we need to add them together. Okay, so we have 2 here. Right, 2 is returned. Right, and here we have 1, and we need to multiply them together, right? So remember, 2 choice on the left, like 2 choice on the right, 4 combination. 2 choice on the left, 1 choice on the right. 2 times 1 is 1 combination, right? 2 choice on the left, 1 choice on the right. So like 2 combination, right? Like A, B, and then I, right? 2 choice on the left, 1 choice on the right. 2 combination. Why? Because we have AI and BI, right? 2 choice, 1 choice, 2 combination. Right? 2 times 1 is 2. Right? So this is 2. Right? So we can move on to this case, right? When 2 is the root here. When 2 is the root, right? Well, yeah, we have one option on the left and one option on the right, right? But if the trees only have one node, we can just return 1, right? 1. We have to multiply them together, it's 1, right? So this become 1. Okay, so we come here, right? If 1 is the root, we have 0 choice on the left, right? So we return 1. For 2, well, it's exactly the same as this, right? 2, you're gonna have 1 and 2, right? 1 and 0, right? This will return 1, multiplied by 1, 1, it is 1, right? Plus, so this will return 2, it is 2, right? I'll arrange this, remember? Right, if n is 2, then the root can be either 1 or 2, right? If the root is 1, we return 1. If the root is 2, then we have one choice on each side, right? Which is leave us one combination, right? And we need to add them together because we have 2 roots. Give us 2 here, right? We need to multiply 1 and 2, then we got 2 here. So finally, we add this together, so we have 5 combination, 5 possible, 5 unique substitutes. Right, I'll put this 5 here, okay? So next, as we can see, we have repeating subtree here, as you can see, right? For this one, right? Pretty big subtree here. That's why we have very bad runtime. So if we use if we apply dynamic programming, we can reduce the runtime to O of n, right? We can store the result. So the maximum number of time we're gonna see each node is 2 times, right? Which is this gonna become O to n, right? Which, we ignore the constant, so it's O of n, right? So we have n, this become n, so n times n is n squared. So if we use dynamic programming, we can reduce the time complexity to O of n squared. All right, so let's code this up. So we're gonna have a helper function for cloud, right? Equal to we're gonna type in m because we already have n here, right? So the n you can return off like this. Okay, so if m is less than 2, right? We can just return 1 because we only have one combination, right? If we have an empty tree or a tree which is one node, otherwise we're gonna count, right? So for I equal to 0, that's not equal to, we have to start from 1, right? From m to m, plus plus, and then count plus equal to count of hello. Yeah, okay, so we need to multiply, right? The choice on the left and the choice on the right, right? If the root is at I, which means whatever on the left side of I minus one, will be our remaining choice, right? And whatever on the right gonna be n minus I, right? So if we have 1, 2, 3, 4, 5, and 4, 5, and I is here, right? So whatever left, this is 2, right? Whatever left gonna be I minus 1, 0, this is 0, 1, 2, right? I minus 1, which is 1, right? Which is you can go like 0 and 1, right? And n is 5, right? 5 minus 2 is 3, which is this index here, right? So the this one is referring to the index, right? So I minus 1 is index 1, right? So you can go up to index 1. It is n minus I, so 5 minus 2 is 3. So you can go like from index 3 to the end, right? Okay. So we multiply the left number of choice multiplied by the right number of choice that we have, and we just add it to. We need to add them together, right? For each and single root, each and every single root. As we call this root, right? It's more clear. Root, right? So if we have like a number from if the tree have a number from 1 to n, right? Which means that the root can either be 1, 2, 3 up to n, right? Okay. And we will have to return a cow at the end. Okay, so that's pretty much it. Let's run this, and it passed, right? But it is a brute force of approach. We give us a very bad runtime, remember? So if I increase n like to 10, let's see what happened. Still accepted. Let's go to routine and 19. Okay, 19 is the maximum. We can go here, which give us like it takes like a long time, right? Almost 3 seconds. So let's try to apply the dynamic programming here using memoization. So we can just store the file, the memo, right? You just have to store the cow for the m before we return the counts, right? So we can store it by memo of count equal to memo of m equal to count, right? So if it is 1, then we say okay. If it is 2, then we can say 2, right? If n is 2, if the variance tree have two root, then you're gonna have two possibility, right? And we can return as at the end, or we can return memo of n. Okay. And in here to set time, right? We can just if n is in memo, we can just return memo n. Right? So we don't have to look at we don't have to compute the subtree again. So it is almost 3 seconds. So let's see. Now we only have like 45 seconds, right? Which is like a huge improvement, like 20, 30 times. Okay, let's submit, see it passed, and it worked. Yeah, so it is a top-down approach, right? We go from the top to the bottom, starting from n, but we can also solve this using a uh, bottom-up approach, like tabulation. So we don't have to use we can save some space, right? We don't need to use a recursion stack with very fast child for Stack Overflow, right? So you can iterate through the um the root, right? So let's say we have an array from the TP equal to array from +1 fill 0, right? We start from the default value is 0 because in the word side we don't have anything, right? And n+1 because we're starting from 1, not 0. So we can set dp0 equal to 1 and dp1 equal to 1, right? So np3, one combination, one choice. 3 with one node, also 1, right? So we can just start from 2 up to and equal to n, or let j equal to 1, j is less than equal to I, j plus plus, and dp of I is equal to dp of j minus I multiplied by dp of I, right? It is j minus 1, and this is I minus j, right? And we can just return the dp of n at the end. Okay, let's see what's wrong here. So the outer loop is the root, right, that we have that for the input, right? So we have the root. We can start from 0, 1, and we're starting from 2 up to and equal to n. And for each I, so if I is the subtree, right? If I is the root, then we need to okay, we need to iterate up to I, right? So let's say I here, I is the root, right? Let's say we have 4, right? And I here we're starting at 2, right, or 3, right? So now n is 3, this n is 4, right? The n is 3, so this I, right, also equal to n. So we need to iterate like from 1 up to n, which is I equal to 1 up to and equal to I here, which is 3, right? So we can try like all possible root, right? And here, so we have 1 to I, right? So 1, 2, 3, I is 3, right? So if we pick this one as the root, right, which means j minus 1 is whatever on the left, and then I minus j is whatever on the right, right? Okay, and then we need to add them together, right? We forgot to add them together for each root from from j equal to 1 to j equal to I. So in this case, we don't need to use the recursion. Okay. J minus 1, j I minus j. Not a number. Why is it not a number? Wait. Okay, yeah, I don't know what's wrong. I'm just gonna like give this a refresh to see what happened. But it looks like right to me. Uh, wait, why is it not working? Why is it undefined here? Wait. Oh, okay. It's just syntax error here. Okay, yeah, now it works. Let's try with like 19. Yeah, 61 milliseconds. So it's pretty fast. So let's submit. And thank you for watching.